Alright, if you notice that on the last video about proofs, I proposed some relatively easy, I should say, proofs. Now today I decided to upscale the difficulty a little bit. So here I have two examples of proofs that I will show you. So first we need to prove that the product of two or more consecutive natural numbers is always even. Now let's just divide this into two cases. Let's just divide. The first one is when there are two consecutive numbers. Two numbers, I should say. So let those numbers will be n and n plus 1, since they are consecutive natural numbers. So therefore our product will be n times n plus 1, which is equivalent to n squared plus n. Now let's just observe this. Notice that n here could be either odd or even. So let's just observe both cases. So let's say n is odd. Therefore, we have an odd number squared. I'll just write O for abbreviation of odd, plus another odd number, and you know that an odd number squared is always odd. So here we have an odd number plus an odd number, which is even. Now let's just observe the case when n is even. We have an even number squared plus another even number, and then we have even plus even, which is obviously even. Another way to approach this same conclusion is by noticing these two numbers. And if you notice by the pigeonhole principle, one of these numbers will be a multiple of 2, and hence its product will also be even. However, I think this method is pretty doable for beginners. Now let's just show that this applies to more than two natural numbers. So let's say the numbers will be n plus 1, n plus 2, all the way up to, well, let's just say we can have n plus x, I should say. So therefore our product will be n times n plus 1 times n plus 2 times all the way up to n plus x. Now I want you guys to take a moment of what's happening in this expression right here. Well, notice that we have proven that the product n times n plus 1 is even. So here we know that this tiny bit of this product will be even. And if you have noticed that if you have an even number times an odd number, it is always even, and then an even number times even number is always even. So no matter whether this is odd or even, the result of this product will always be even. And hence we have proven this for more than two natural numbers, and we have fulfilled our criteria, and so we are done. Let's just put a little box there. Now next, for part B, we need to prove that the binomial coefficient n choose 4 is an integer. Now the form n choose r could be expressed as n factorial over r factorial over n minus r factorial. This notation, or this symbol, is often used in combinatorics to count the number of combinations of certain things. And I should say here that n is greater than or equal to r, which are both integers. So let's just work things out for this question. Using our derived formula for n choose 4, we have n factorial over n minus 4 factorial times 4 factorial. Now we can cross this and cross this out to leave the numerator with n times n minus 1 times n minus 2 times n minus 3. And notice that 4 factorial is 24. However, let's just express this as 3 times 2 to the third, or probably 3 times 8. Now, our statement is equivalent to proving that this expression is divisible by 3 and 8 simultaneously. Let's just work out for this expression being divisible by 3, since it is the easiest one. Here, notice that by the pigeonhole principle, at least one of these numbers will be divisible by 3. And with the special case of two of these numbers being divisible by 3, which are when n and n minus 3 are both divisible by 3. However, this approach can be approached in another way, which can be also from modular arithmetic. So let me just do that for you guys. So we can have n to be congruent to 0, 1, 2, or 2 mod 3. And now the usage of this equivalent sign is different from like most other algebraic statement proofs, I should say. So this one in modular arithmetic context refers to the remainder, or I would say the residue of a number divided by a certain modulo. While the equivalent statement in certain algebraic statement proofs implies that it is a strict statement. It works for all inputs of any variable. Alright, so that's about that explanation. So here, when n is congruent to 0, well, we're done, because this will be congruent to 0 and that will make it divisible. If n is congruent to 1, then it would make n minus 1 divisible by 3. If n is congruent to 2, it will make n minus 2 n minus 2 divisible by 3. And hence we have covered all cases and we are done. Next and finally, we must show that this is divisible by 8. Alright, this will be a little bit tricky, but we know that by the pigeonhole principle, we know that exactly two of these numbers will be divisible by 2. It could be n or n minus 2, or it could be n minus 1 and n minus 3. And furthermore, among two of these possible numbers that are divisible by 2, one of these numbers will be divisible by 4. And without loss of generality, assume this is divisible by 4. Therefore, n will be divisible by 2. Alright, since it is both divisible by 2 and 4, it must be divisible by 8. And so, you can work this out for all the other cases, and we are done. This approach again could be approached similarly by using modular arithmetic. So you can suppose that n could be congruent to 0, 1, all the way up to 7 mod 8, and then just cover all the cases. And hence we have proven that n choose 4 is an integer, and we are done. And this also ends this video.